And this is a 5 week long series. If you have not seen the agenda of our training, what you see here is basically title of each of those 5 weeks. So today we are going to talk about remote sensing, fundamental of remote sensing. Next week we'll talk about satellite imageries. In week 3 we'll talk about the aerosols data which can be related to particulate matter air quality, and then the trace gas data sets will be talked in week 4. And in the week 5 basically we will review all the material and then provide you what are the upcoming future satellite missions to help air quality monitoring. So this is so let's talk about fundamental of satellite remote sensing. So the first questions come to our mind is what is remote sensing? So remote sensing is the science of obtaining information about an object or an area from a distance. And one of the simplest example of remote sensing sensor is our eye is actually a natural remote sensing sensors which can obtain information about an object from distance. So this is one of the simplest example. Simple photographic camera is another most frequently used remote sensing sensor, which can capture images and record them from distance. So these are really great example of how remote sensing sensor works and what they really do. Looking more into detail and going into satellite things, so remote sensing instrument again collects information about object or event within the instantaneous field of view. So in this picture what you see here is a object sitting on the earth, which are some vegetations, and then you have a remote sensing sensors uh, installed or located on a suborbital platform like a space like a aircraft or a spacecraft like satellite, and it is looking down, and then when it looks down, the height of the satellite or the plate sensors really does decide a lot of quality and quantity of information you can get. And then the instantaneous field of view also play an important role in deciding how accurately or how precisely you can get certain information about the object. Moving forward, these remote sensing sensors or instruments uh, can be placed in many different platforms. Your application basically help you decide which platform is most useful to you. There are several questions that need to be answered to determine which platform is most useful, such as how much detail do you need and how frequently do you need this information. Uh, these in the pictures, what you see are examples of remote sensing sensors which are placed either on some kind of a vehicle which is moving, and you can make measurements of certain area while moving around this vehicle. So you can put those sensors as well. You can also put the sensors on the balloon, which can fly up in the atmosphere and take measurement in different altitudes or different height in the atmosphere. And these are really very useful when you want to get information about atmospheric component in at a different height. You can also fly airplanes with remote sensing sensors, and they also are very useful uh, for getting a specific information over a specific area. And then the satellite is of course one of the most useful remote sensing sensor which you can put on. I will be focusing mostly on satellite remote sensing in this presentation and discussing how this works in this series of the uh, webinar series. So before we start understanding the remote sensing process, it is important to understand something about the source of energy or the information carrier in when we talk about the remote sensing. So electromagnetic radiations travels through the space in form of waves, and it originates from the, in our case, we are mostly talking about the sun's solar energy. The waves have different lengths in different part of the spectrum. As you can see here in this chart on the right side of the slide, that this electromagnetic spectrum has a different wavelength. Uh, Although we are talking about light, most of electromagnetic spectrum we cannot detect by human eyes. So if you look this spectrum, it is very wide, and visible is just one tiny part of this spectrum, which we or human can see through the eyes. Uh, as you go towards ultraviolet, X-ray, and gamma rays, the wavelength decreases, and as you move from left from the visible, like microwave, radio waves, infrared, the wavelength increases. And for your just to give an analogy to check the size of this wavelength, we have some of the reference material which you can correlate to this length of this radiation. And most of the remote sensing sensors for air quality, specifically for particles, they works in the visible part of the solar spectrum. There are some which can provide information in ultraviolet, and then we also use infrared to detect some other atmospheric phenomena. So this electromagnetic radiation is very, very important in understanding the satellite remote sensing and how it works and how the information is carried. So depending on the purpose, different satellite capture a specific portion of this entire electromagnetic spectrum which we use. Now, the next thing is to understand is how satellite and sensors collect this information. So optical or passive remote sensing depends on the sun as a source of illumination or the source of energy, as we discussed in the previous slide. And this solar radiation, as it emits from the source sun, it passes through the atmosphere and it interacts with the atmospheric component. It also interact with the objects which are located on the surface. So in this case, either it's vegetations, water bodies, bare soil, build up areas, buildings, parks, everything which is located on the surface, the incoming solar radiation interact. And now, once the incoming solar radiation interact, depending on the property of the incoming solar radiation, which means the wavelength, and depending on the property of these objects, it will either absorb by those objects or reflect back to the space. So the radiation which reflect back to the space is captured by the satellite which is sitting in the space. And this reflected solar radiation is measured in different wavelengths with very precise accuracy by the satellite sensors in the space. And the different sensors collect this radiation in different wavelengths depending on what's the purpose of that particular instrument. The intensity of reflected and emitted radiation to space is influenced by the surface. So it can influence by the ocean. If there is a snow ice on the surface, that can influence. Very bright areas such as desert can influence. Forest or vegetation can influence in a different way. So each this surface property type of surface influence the incoming solar radiation in different ways. And of course, the atmospheric condition also influence this incoming solar radiation. Different temperature influence in different ways, amount of water vapor or humidity in the atmospheres, clouds, rain, aerosols or the particles in the atmosphere interact with the solar radiation and influence it. So different wavelength respond to different geophysical quantities and the physical properties of the surface or the atmosphere. For example, significant amount of solar radiation is reflected back to space by snow, ice, or cloud uh, as compared to vegetation. So if you have a cloud or a snow, and that's why we see them very bright object when we look the satellite image. And we'll see some of those example in week 2 when we look into the satellite imagery in more detail. One thing to understand when working with the satellite data is that this reflected or emitted radiation from the Earth's surface must travel through the atmosphere before it reaches to the satellite. So sometime, depending on again application, we have to do this corrections to the satellite data for these atmospheric conditions, and in most cases, we have to perform this kind of correction. So to make sure that we are retrieving information which is relevant to our use. And this atmospheric corrections are often very useful for air quality studies because uh, for air quality we are trying to obtain information about the particle or gases which are in the atmosphere. So when we talk about the air quality information, instead of correcting for the atmospheric condition, we have to correct for the surface conditions. So if surface is bright, if there is a vegetation, we have to take into account the contribution from the surface and take out that from the total signal. So depending on your application, whether you're trying to get information about the atmosphere or land, you have to make corrections either for atmosphere or for the land. For air quality application, we have to mostly do correction for the land, and of course for atmosphere as well. Again, it depends on what is our interest within the atmosphere. Either we are looking for clouds or aerosols or trace gas. Um, any of those will require some kind of corrections to the signal. And these corrections we do using theoretical calculation and using other ancillary data sets, and we make some assumptions as well. So once satellite make measurement of this radiance in different wavelength, which we call spectral radiance, we use a priori information and ready to transfer calculations to generate simulate what satellites should supposed to make measurement, and then we combine these two pieces of information in something we call retrieval algorithm. And these algorithms are mostly inversion algorithm, where we try to match satellite measured radiance with a priori or theoretically calculate radiance and come up with the geophysical quantities such as temperature, wind speed, water vapor, relative humidity, uh, aerosol number of particles, concentrations, or trace gas concentrations, or aerosol optical depth, which is term which we often use for air quality and which will go into more detail in week 3. We retrieve this geophysical parameter, and since it does involve a prior information and theoretical calculation, there are some assumptions which goes into that, and that can create some of uncertainty in the retrieval of these geophysical parameters. So different product have different uncertainties or different errors in their when from a specific satellite or a specific algorithm, which needs to be taken into account when we use these data sets. And depending on what product and we can apply for different applications. So we can use this product, for example, to monitor smoke from certain region, or how the smoke is transporting, or how dust is transporting from Saharan desert to over Atlantic and to the east coast of United States or in some other parts of the world. So those kind of application can be very easily done using the satellite data, and we will see those more example as we move forward in the webinar series in week 2, 3, and 4. Now let's do very quickly a break and quiz before we move on. So I have few questions here again in form of poll, and let's take about 30 1 minute time to answer these. Uh, and these are just based on what we have looked so far in terms of the number of in the slides. And there are three questions. One is the remote sensing instrument can be installed on the rooftop of a building. True or false statement. Second is the incoming solar radiation in all wavelength interact with the Earth atmosphere system in an identical manner, or so again true or false statement. And then satellite can carry multiple sensors on board. This is something which we haven't discussed, but just make a guess, and then we will discuss this a little bit more in coming slides. So just few more, maybe 15 more seconds, and then I will close these three questions. Okay, so let's uh, the remote sensing instrument can be installed on rooftop of building. The answer is true. Again, it depends on the instrument, technical aspect, and what we are trying to do. So the correct answer is true. The second question is incoming solar radiation in all wavelength interact with Earth atmosphere system in identical manner. This is a false statement. So they does interact in different ways because it depends on the wavelength, and it also depends on the property of the Earth atmosphere system. And the third question is a satellite can carry multiple sensors. Most people have answered it correctly. It's yes, it's a true statement, and we'll talk about that a little bit in a few more slides. So with that, let's move on to continue. Let's talk about satellite sensors and some of the orbits. Some of this terminology is important to understand because when you start using the satellite data, you will often hear these terminologies. And if we don't understand, we can misrepresent the data, and we can misinterpret the results of our analysis. So, uh, Earth observing satellite typically have names such as the one listed here. There are aqua satellite and aura satellites, and these remote sensing instruments actually. So there are two terms here. One is satellite and one is sensor. So the satellite is basically a platform on which we install sensors or instruments. So satellite is kind of a carrier for the sensors uh, on which we install these sensors. So satellite can be one satellite can have multiple instruments. In this case, for example, in aqua satellite we have 6 instruments, and on the other hand we have another satellite, aura satellite, which have 4 instruments. Aqua satellite, the two of the highlighted MODIs and AIRS are sensors which provide some kind of information on air quality. The Aura satellite is designed to actually get information about atmospheric chemistry, and it has 4 different instruments which provide different pieces of atmospheric information. For example, OMI is ozone monitoring instrument. It is designed to monitor atmospheric ozone. It does also provide information about absorbing aerosols and other things. And then there are other instruments which does provide different pieces of information. So remember, the satellites are the platform on which sensors are installed. So sensors are also called instruments. So when we talk about the specific data, it comes from the specific sensors or the instrument, which can be on board on either one satellite or multiple satellite. And we'll see example of that in coming weeks. Satellite and sensors can be classified or characterized in many different ways. Uh, Satellite we can classify it by their orbits. We can characterize by its source of energy. We can also characterized by in which part of the solar spectrum they make the measurement. There are different measurement techniques which can also be used to classify these sensors. And important thing is the resolution, and we'll talk about this thing. There are several different types of resolution which can also be used to characterize this instrument. And the last but most important is the application. You must have heard the term weather satellite, land satellite, ocean satellite, atmospheric satellite. So depending on, or radiation satellite, depending on what is the purpose of that satellite, a specific satellite mission, we can actually classify them in different based on the application. And I'll discuss this some of this in upcoming slides. Before going into details, one other thing which is very common is orbits. So there are primary two types of orbit: Earth observing satellite, so as the geostationary orbit and low Earth orbit. In the low Earth orbit, the common orbit is called polar orbiting, and then there are few others, non-polar orbiting, which is not relevant to the air quality right now, so I'm not going to talk into more detail about those. But the geostationary orbit is generally a high Earth orbit, which approximately about 36,000 kilometer above the Earth's surface. So any satellite which is in the geostationary orbit is located around 36,000 kilometer above the Earth's surface. It is always in the same position with respect to the rotating Earth by orbiting at the same rate in the same direction as the Earth. So the satellite, in following those rules, appears stationary corresponding to a specific region of the Earth. This geostationary or geosynchronous satellite provide frequent measurement and are extremely valuable for weather monitoring because you can get a constant view of the same surface area with high frequency every 10 minutes, 30 minutes, 1 hour, depending on what satellite you are talking about. They provide. Since these satellites cover only one area on the Earth, several satellites are needed to cover the entire Earth. So the limitation of geostationary satellite is they are located over one specific region. For example, United States has a geostationary satellite called GOES, which does provide image like this, which is shown here on the left side every 30 minutes or every 1 hour, but it's only over this region. It does not provide cover any other part of the world. So these are the limitations of the geostationary satellite. Most Earth remote sensing satellite or low Earth orbit, which is, and these low Earth orbit are basically polar orbit. Polar orbiting satellites provide a more global view of Earth. These satellites move around the Earth from pole to pole, as you see in the picture here. They move, and then the Earth, as the satellite moves around the pole, the Earth turns underneath it and allowing complete coverage of the Earth. So instead of satellite rotating around the Earth, satellite rotates pole to pole, and Earth underneath it rotates, and that way it gives it the satellite sees different part of the Earth in different time, and that's how it can cover different part of the Earth. The satellite passes the equator and each latitude at the same solar local solar time each day, uh, meaning that satellite passes overhead at essentially the same local solar time throughout all the season of the year. So this actually enable regular data collection at consistent time as well as long-term comparisons. So polar orbiting satellite does make uh, almost daily, depending on again other factors, global measurement at the same solar local time. So this basically provide a consistent long-term data series which we can use for applications such as trend analysis and other other understanding other features of the atmosphere. Here an example of showing the difference between geostationary and polar orbiting satellites. So what you see here is a PM 2.5 microgram on the y-axis and then the time on the x-axis. And this is just an hypothetical case where if you have a geostationary satellite, you can get every 30-minute, 1 hour observations throughout the day time of the time. But if you have a polar orbiting satellite, then you will only get one or two or three, depending on how many satellites you have in the orbit. So here we have this vertical lines represent one observation from Terra satellite, which is again a air quality sensors. Air quality satellite which carries several sensors, and it does provide you a morning observations. There is another satellite Aqua which we see earlier, provides another observation at 1:30 in the afternoon. So you get global coverage from the polar orbiting satellite, but less frequent observation, whereas you get more frequent observation from the geostationary, but you get only a specific area or region covered. Some of the upcoming geostationary satellite specifically designed to do air quality monitoring are Tempo from the United States, NASA, James from the Korea, Sentinel-4 from the Europe, and they will form a constellation of satellite, which we'll talk more details into week 5. The swath width or the coverage is another important aspect, and this determines their frequency of observations and the global coverage. So this is defined by the spatial extent of the satellite orbit for which the measurements are taken. Here is the comparison of the spatial coverage across the surface of the Earth from the most common sensor used for air quality application, specifically for monitoring aerosols or particulate matter. So what you see here are 4 different sensors which does provide information on atmospheric aerosols. The Weir's instrument is have a swath width of about 3000 kilometer. MODIS instrument, which is another instrument which we'll talk a little bit more into detail in week 2 also, has about 2300 kilometer swath width. And then Miser, which is another instrument which has multi-angle capabilities, is 380 kilometer swath width. And then we have a Calypso, which is a active lidar in the space, has very narrow swath width. It's almost a 1 kilometer because this is an active sensors. And again, we will talk about this when we go into the aerosol product in week 3. But what is important here to understand is that different sensors have a different swath width or the spatial coverage, and that actually determine their global coverage, their frequency of observation over particular location, or the detail of the information they can get about the air quality. Here an example of these 3 sensors which we just talked in the previous slide. So if you look the MODIS 1 day coverage, then what you see here is on the top is basically this is 1 day coverage of MODIS, and what you see this black area are the gaps in the data due to the orbit gaps. So and then when you go to the Weir's, which has a wider swath, 3000 kilometer as compared to 2300 kilometer compared to MODIS, you see there are no gaps in the data. Okay, so all the during the daytime area over the entire globe is covered by the Weir's. So this is a 1 day coverage from the Weir's. So Weir's has a much more coverage than the MODIS. And if we go to the Miser, which has a 380 kilometer swath width, then you can see that there's a huge area. This all this black area is actually data gaps in the Miser. So because of this narrow swath width of miser, it does take longer time, 7 to 8 days, uh, to cover the entire globe. Uh, and this time period also varies over actually different latitude wells, depending on where you are interested on the surface of Earth. Another important aspect of satellite remote sensing is to understand whether the sensors are passive or active. Uh, Most of air quality sensors are passive, except few of them. Uh, Remote sensing systems that measure naturally available energy are called passive sensors. So in this picture, you see a satellite is there. It's making measurement of the Earth atmosphere system, but it is using sun's energy to make those measurements. So sun's energy, like we talked earlier, go through the atmosphere, get reflected back to the space, satellite makes measurement, and that's how the passive sensors make the measurement. It does not have its own source of energy. It uses sun or earth emitted radiation. Some of the examples of these passive sensors, which we just looked previously, MODIS, MISR, OMI, VIRS, these are all passive sensors. On the other hand, active sensors emits radiation that is directed towards the target to win object or any component on the Earth, which we need to get investigated or which about which we want to obtain information, and then that radiation reflected back from that target and is detected and measured by the sensor. So active sensors have their own source of energy. So they are most likely lidar or radar, which transmit energy or electric radiation in certain part of the solar spectrum band, and then it travels through the atmosphere, interact with the atmospheric component or the land surface on the earth, and then reflect back to the sensor. And then there is a huge telescope mounted on the satellite, which capture that radiation which is reflected back. And by making that measurement, you get more accurate information, because in this case we are our source of energy is known, very well characterized. And this also helps to get the, because this energy, depending on the time to travel it back, we can estimate different layer of the atmosphere. We can get the information about different layers of the atmosphere or different altitude. Calypso is one of the example of such satellite, is a true wavelength active lidar in the space, which does provide important information about clouds, aerosols, different types of aerosols, and many other information which can be relevant for air quality monitoring, specifically transport activities in different altitude of the atmosphere. Okay, moving on to the resolution. Resolution are also very important aspect of satellite remote sensing, and there are different types of resolution: spatial, temporal, spectral, and radiometric resolution. And we'll go by one to these and see what they mean. Depending on the satellites, its orbit configuration, its sensor design, they can be different for different sensors. And this is one of the most important aspect when we use the satellite data for air quality application. Before defining this resolution, I would like to define a term which you will often hear when you use the satellite data, is called pixels. This is the smallest unit of an image, in simplest word if you want to learn it. So what you see here is on left is an satellite image, and if you take any part of this image is divided into array of this small unit, and each of this unit is called actually a pixel. These are the smallest unit of this image. They are arranged in column and rows, and every digital image is basically comprised of two dimensional array of individual picture elements, and these are we called pixel. uh, and this is more a technical definition, Uh, but essentially, each of these pixels represents certain area on the surface of the Earth. Each pixel has an intensity value and location address in terms of latitude and longitude in this two-dimensional image. The spatial resolution of any satellite or any image is defined by the size of this pixel. So this pixel size could be in centimeter, meter, kilometer, depending on what satellite we are looking at. So, and to look into more detail about the importance of the size of this pixel or the spatial resolution, here I have a picture taken by uh, a low orbiting platform such as the aircraft in different spatial resolution over a locations on the earth. What you see here, the first image is taken by a instrument which has a spatial resolution or a pixel size of half meter resolution, and what you can see in this image very clearly, all the different features on the earth's surface. As we move to the right of these images, the spatial resolution start decreasing, or the pixel size, in other words, started increasing. So 1 meter, 2.5 meter, 5 meter, 10 meter, 20 meter, and it goes up to 80 meter. But what you see here is as we start increasing the pixel size, or as we start, in other words, decreasing the spatial resolution, the clarity or the ability to distinguish different part of the image clearly we start getting the image more fuzzy or haziness. So you can see at 5 meter resolution you can still see some features, but when you go to the 10 meter resolution things get started very fuzzy, and it really depends on how much detail you want to get information about this thing. So spatial resolution really plays an important role in identifying different features on the Earth surface. Spatial resolution is more important when we try to get information about the land surface. Here are some of the sensors which are used for air quality application, and their spatial resolution varies from 250 meter to 13 by 24 kilometer, again depending on which sensor and which product we are trying to use. Another term is spectral resolution. Spectral resolution describes the ability of a sensors to define the fine wavelength interval. The finer the spectral resolution, the narrower the wavelength range for which a particular channel or band is making measurement. That in this example here, there are two different example. One is the black and white. So if you have a band which is all the way starting from point 4 to point 7, and what you will get in the entire band is basically black and white film type of. So you have a bandwidth which is very broad all the way from point 4 to point 7 nanometers. So the value you will get is only black and white film type. But if you divide this same bandwidth into three different spectral band, blue, green, and red, and you can make measurement in this specific band, then you get three piece of information. And when you combine these three pieces of information, you get a colored picture of the same scene. And we will see this more into detail when we go to the week 2 and understand the satellite imageries. Uh, Typically, there are two types of instrument: low spectral resolution, such as MODIS, and then there are hyperspectral sensors, which are like OMI and ARS. So these hyperspectral sensors make measurement on every single wavelength. They have a spectral resolution of 1 nanometer or higher, whereas this low spectral resolution sensors, MODIS, they have a spectral resolution of 20 nanometer or more than that. Here is an example of a spectral resolution important. So again, if you want to get information about the specific geophysical quantity on the earth or in the atmosphere, then depending on their spectral behavior for that interaction with incoming solar radiation, you will need different type of spectral resolution. So if you have a broadband instrument, then it will be very hard to differentiate between the different classes. But if you have a narrow band instrument, hyperspectral instrument with high spectral resolution, then you can actually differentiate between different classes. So spectral resolution becomes very important when we want to separate things in the atmosphere or on the Earth's surface. Another important is radiometric resolution. These image data are represented by basically positive digital number that varies from 0 to uh, a selected power of 2, less than 1 of that. And the maximum number of brightness level available depends on the number of bits used to represent the energy recorded. So whenever the satellite make measurement, it records the energy in terms of the voltage and in terms of the digital numbers. And depending on the technology which has been used or the space available for storing the data on the satellite, you can assign some certain number of bits for each measurement to be recorded. Larger these numbers, higher the radiometric resolution and the imagery become sharper. So here we have a just an example. There are 1 bit, 4 bit or 8 bit sensors. So if you have 1 bit, so you will have only two levels, 0 and 1. So you can only see, say, black and white. But if you have a 4-bit sensor, then it will have a total 16 levels, 0 to 15, and then you can see the shades of black and white on this. If you increase the number of bits used for recording, for example, if you use 8-bit, then you will have a 256 levels where you can actually see many more shades of black and white. So similarly, the current air quality sensors, modis measures are 12 bits, so they can have close to 4096 level. There are other sensors which has a different number of bits and they can record the image. So again, the radiometric resolution is important in uh, how precise the measurements are. Again, here is an example of how the radiometric resolution can affect. The first picture is taken using the two levels, so you can see only black and white, like I said earlier. The second picture is taken using four level sensor, so you can see some shades of black and white, and you can start looking into different features. But if you have a sensor with 8 or 16 levels, then you can actually start looking into specific features on the Earth's surface, and you can see the different shades of black and white. So just imagine when you have a 4096 level from the MODIS sensor, you can do distinguish a lot more features, and that's the beauty of satellite data actually. When we use this high radiometric resolution sensors to do the air quality work. Temporal resolution depends on the swath width, as I explained earlier. In this picture, if you see this bit of this orbit across this, this is defined as swath width, as I defined earlier. So temporal resolution is defined by how frequent a satellite can provide observation on the same area on the Earth. It mostly depends on the swath width of the satellite. Larger the swath, higher the temporal resolution. Uh, Typically, polar orbiting satellite provides 1 or 2 days in a repeat cycle or the temporal resolution they have, whereas the geostationary satellite, which look at one place on the Earth, continuously can provide much more high resolution, high temporal resolution data, ranging from 10 minutes to 1 hour. There's a trade-off. We call it remote sensing trade-off. It is very, very difficult to obtain extremely high spectral, spatial, temporal, and radiometric resolution at the same time. So depending on your application, depending on the purpose of satellite or sensor, be compromised by one of this resolution. So for example, MODIS does compromise on the spectral resolution, but it has very high spatial resolution. On the other hand, OMI sensor compromise on the spatial resolution. It has a 13-kilometer resolution, but it has a very high spectral resolution. And we do that because purpose of MODIS is to detect this big picture type of things, cloud aerosols. On the other hand, purpose of OMI is to detect this small uh, quantities in the atmosphere like ozone, NO2, SO2, which are specifically sensitive for specific narrow bandwidth of incoming solar radiation, and to make those measurements we need very high spectral resolution. So we always compromise with one of this resolution when we talk design any specific sensors depending on the application. Okay, so I'm almost done with today's presentation. We have few more cues to take, and then we will take some question answer. So the first question is, which satellite has higher spatial resolution? We talked a little bit about this, so and you might have seen that in few of the slides. I noted. Again, the second question is Sensor's ability to discriminate very slight difference in recorded energy is described as we just talked about it. And then another question is frequent observations over a certain region can be obtained by which type of satellites. So this depends on whether it's a geostationary or polar orbit. And the last question is basically true false. Geostationary satellite can provide global coverage. So these two questions are interrelated actually. So let's take a minute of time to answer this, and then I have few more slides to go over, and then just some informative slides, nothing, and then we'll take question answer. Okay, so the first question is, which satellite has higher spatial resolution? So since we did not talk specifically about the Landsat, but it was mentioned on few of the slides. But Landsat has higher spatial resolution. Its current Landsat data has 30-meter resolution, whereas the MODIS is 250-meter resolution. So the correct answer is the Landsat. Although we do not use Landsat for air quality application, but sometime you can use for the surface mapping. The sensor ability to discriminate very slight difference in recorded energy is described by. So we talked about the recording of energy in terms of the bits, and those bits are related to the radiometric resolution. So the correct answer is the radiometric resolution. The next question is frequent observations over certain regions can be obtained using which satellite? And the correct answer for this is the geostationary, because we are talking about hourly observation, and to do that, the satellite has to be in the geostationary. Polar orbiting satellite cannot do that kind of thing. So the correct answer is geostationary satellite. And the last question is true false statement. Geostationary satellite can provide global coverage. So again, if you answered this correctly, the previous question, this should be very, the answer of this is false. So geostationary satellite cannot provide global coverage. They can only provide coverage over certain area. Polar orbiting satellite does provide global coverage. With that, let's move on, and I want to provide you some more um, basic information. So I'm going to move these questions away. Next week, we will talk about the satellite imageries, how to use for a certain air quality application, what it means for information content, how to identify different features, and then we will also do a hands-on exercise for near real-time image access using a tool called worldview. And then we'll go over some of the application, how we can use worldview to access near real-time satellite imageries. Here are some of the reference, and if you which we used to create some of the material which we presented today, and some of the, if you're really interested in learning more about some of the terms, or if you by any chance did not understood a specific terminology, or want to really learn more about fundamental of satellite remote sensing, then there are several very useful tutorial online with graphics and a lot of text for explanation, which you can go through, and some of them are suggested here. The good news for this is there is no assignment for this webinar series, so we will not have any assignment. We will try to have this quizzes in each session, but we will have no assignment for you to work on. Uh, we get often request for the certificates and questions. So in order to receive the certificate for this webinar series, you must attend all the sessions either live or by using the recording which we put on our website. And when you see the recording, we keep that record. Our software does record that information, how much you have watched that recording. So based on those two criteria, we issue the certificates. So please, if you are requesting for a certificate, make sure you have fulfilled these conditions. This is must required to issue a certificate. All the materials and the recording from this webinar series will be available on this link here. Uh, you can access agenda, recording, PPT, everything from this website, which is ARSET website. And then again, I have a contact information. If you have a technical question from the today's session, you can contact me. If you have a specific logistic questions, how to access material, if you're and trouble in finding a specific material, you have question about any upcoming future trainings or any other software related trouble, please contact Brock Blevin. He will be happy to help you. With that, I will be happy to take questions if you have. Thank you. You can type in your questions here in the chat window, and I will try to answer them as much as I can. So the first question is, outside the NPP, Sumi and Landsat, most NASA USGS LEO satellite I can think of have exceeded their expected life. Can you give me more detail on upcoming US missions tempo? In particular, there will be a follow-up to MODIS outside VIIRS. Okay, so basically we will talk about all these issues in the week 5, but just to briefly answer your question, yes, Tempo is a mission which is going to be launched in about 2020. The expected lifetime of Tempo will be about 5 years, and it's specifically designed to address several air quality issues in the US. MODIS is designed for 3 to 5 years, and it is giving data for last 15 years. And there are two MODIS sensors. Now we have a The next generation, the Modis does not have exact follow-up, but it has wears which is provide almost similar information, not exactly the same, but almost similar information as Modis. And wears will have follow-up missions. So there is a it's a NOAA NASA partnership mission. There is a currently one VIRS which is launched in 2010 is working. In 2017, I think next year another VIRS will be launched on just another NOAA satellite, and there are more VIRS instrument which are already planned for upcoming missions. So VIRS will have continuous measurement for next 20-30 years, I would say, but not exactly like Modus. It has slight differences. And we'll talk those more details in week 5. Okay. Another question I see is, since OMI has 1324 kilometer resolution, would it be possible to detect a specific constituent emitted from industrial stake? Okay, this is very interesting question. So yes, OMI's spatial resolution is coarse. Detection of this emission from industrial stick will depends on how consistent that emission is. So we and are there any other source of similar emission in that region, that will determine. So if you have only one industrial stake and there is no major source around that, then what we can do is we can accumulate data over time from that coarse resolution OMI sensor, and we can actually, because some of these emissions are short-lived, so they will usually found near the source only, and that way we can actually detect some of this, but it has a limited application and probably need specific data processing before detecting that. Some of the example I can give you for this is, there have been a lot of fracking activities, and when we do the fracking, sometimes there are gas flares burning happens, and in many cases we can detect these gas flares actually from using OMI data by combining data over the time. And if you are really interested in that aspect, please email me and I can forward you some of the papers where people have tried to do that kind of activity. Okay, there is another question. I think this is related to the Python code for comprehending models data for AOD possible. Yes, we have. I am not really 100% sure if I understood the question, but we do have a sample Python code on our website which can read the models errors or data. Okay, so there is another question which says why we don't use high spectral spatial and high spectral spatial and radiometric resolution. Uh, the brief answer is that it's very hard to achieve all the resolution technologically, uh, and then there are economical constraint also. When you start implementing this very high spectral spatial resolution radiometric solution, things become very expensive, and sometimes you don't really have uh, sometimes doesn't really require to have those kind of things. But as technology is advancing, we are getting it better on getting all kind of resolution at higher resolution. Hyperspectral data is very discriminating on data. We learned that Hyperion will be off next year and other replacements. Okay, I'm not sure if I understood your question. So if you want, maybe you want to rephrase it. Can we model different type of air pollution sources like point source, area source it using sensors. We will talk about that in week 2 and week 3. Again, depending on what kind of pollution we are talking or what kind of source we are talking. Up to some extent, we can do that, but not at limited level, depending on the resolution which sensor which we are using. So for example, we can probably differentiate between biomass burning and dust type of aerosols and industrial pollution aerosols, but we may not be able to distinguish between industrial and emissions from the cars or vehicles. There is a suggestion, can you make a class on Python? Uh, Python is very popular language, and if you Google or search online, you will find very useful tutorials. We have done a hands-on exercise using Python in our advanced webinar, and if time and resources permits, probably we will do more trainings which will use Python codes to uh, extract the satellite data. Okay, so another question, why Landsat is not being used for air quality? Uh, Difficult question. Uh, Landsat is very high resolution and it has very it's designed to do the land mapping. It's 30-meter resolution. First of all, its coverage is very limited. It does not provide, it takes around 16 days to provide a global coverage. Second is when you work with this very, very high resolution data, then the signal to noise ratio becomes very issue. And retrieving aerosol information or any other air quality information from Landsat can be very uh, can have large uncertainties. It does not mean that people have not tried using Landsat for retrieving aerosol information. There have been a number of attempts have been done in past, uh, but there is no people have shown on a research basis it can be used to get the aerosol information, but there is no operational product from for air quality from the land side. But that's an area not exploited fully, and if you are interested, I will be happy to help you with that aspect because that's if we can get that high resolution air quality information, that will be really good. Okay. Okay, I see a message from New Zealand. Thank you for attending. I know this is night time there, but I appreciate your time and interest. Okay, there's another question. How calibrated these sensors are with passage of time? Okay, so yes, that's very important question. When this satellite, like I said, designed for 3 to 5 years to work, uh, it is very important to make sure that these sensors are stay their quality does not degrade over the time. Quality of these sensors and measurement quality does degrade, so there is a specific team of people actually who make sure that the sensors are calibrated and there's no problem in that. Some sensors have onboard calibrations. They do once in a while calibrate with the moon or other source in the space or on the ground, such as which are relatively constant over the time. Uh, and there are other lab-based calibration which we do pre-launch. Uh, Sometimes we have to make adjustment to the calibration coefficients. as you mentioned that as time passes, the uh, quality or the life of the sensors degraded, and to make sure their performance or their quality of the data they are providing is high, we have to continuously keep an eye on the calibration. Do some census data overlap? If so, which information used over the others and both use? Okay, yes, many census data overlaps, and the beauty of that is each census provide different piece of information. So if we can combine information from different sensors which overlaps, then we can understand different features about specific objects or specific events in the atmosphere. Another question, can we use MODIS or Landsat to estimate air quality over city? The answer is yes. And to learn a little bit more about that, we'll talk in week 3 and 4 for on that more details. Okay, there is a question on slide 22. Okay, I have to open the presentation. I don't remember what slide 22 is. Uh, okay, I think those are all geostationary, just demonstrating how the geostationary satellite can make measurements. So you can consider uh, each color as a different geostationary satellite. It's just to show how things should work. Another question, do you combine data from the different instrument? Yes, very often. Because each instrument, like I said earlier, provide specific information, and if you want to understand complete picture or answer several questions, then often we have to combine data from different sensors. With geostation satellite, any differences at night time? Also, why does Miser operate at an angle to other sensors? Okay. uh, the geostation satellite does not uh, it depends on what we are trying to do. Okay, so like I said, all these passive sensor, it can be geostationary or polar. If they depend on the solar energy and if they are operating in visible part of the solar spectrum, then they can only operate in daytime. They cannot provide observation in nighttime for the obvious reason, because there is no sunlight. Although there are some measurements like cloud and water vapor and temperature, which can be measured using infrared light, and which is emitted by the Earth's surface and available at the night time as well. So we use that to obtain that kind of information, but not for the aerosols or particulate matter or trace gases. Another question is, why does Miser operate at angles to other sensors? Okay, so Miser is a multi-angle, multi-spectral instrument. It has a 4 wavelengths on which it makes, and then it make measurement of single piece of Earth in looking from 9 different angles. When you look things from different angle, you see a different view of the atmosphere, because you can experience that by yourself. When you look things from one angle, you will see some specific view, but when you try to turn your eyes up and down, then you will see a different view. And same thing happens in the atmosphere. If there is a very thin layer of dust or smoke or pollution in the air, uh, and if you look down, sensor is looking the down, it might miss it, but if you look it from certain angle, you might be able to capture it. So, and also looking at different angles give a sense of height in the atmosphere, and we will talk about that when we'll reach to the week 3 when we specifically talk about some of the air quality. Possible to overcome the limitation of geostationary and polar satellite by placing one obliquely to one of them. I'm not okay. Sorry, I'm not sure if I understand your question. If you can clarify it. And then we have some suggestion on uh, uh, making classes for correction and calibration of the instrument. Uh, Thank you for that suggestion, and we will think about it and see if we can accommodate those kind of webinar series as well. Those are very, very technical, so we have to see how we can accommodate those things. But thank you for your suggestion. And again, I think there are this question about how we can basically superimpose data from different satellites to get different piece of information. Uh, if you are used to the satellite data, then it's really easy to superimpose the data. You have to make sure the time and the spatial coverage matches with what you're trying to do from different sensors. Uh, if you're new to that satellite data, I would not suggest to do that approach, because in order to superimpose data from different satellite, you really have to understand details about the capability of each satellite and what is the purpose. So depending on your purpose, there can be different methods which we can employ to superimpose data from two different instruments or more than two instruments. Okay, I think I don't see any more questions. So if you have more questions, feel free to email me. And if you have other, if you don't have any question, then I will just say thank you again for attending today's session.